In the previous slide, I show you that if you have the coils stationary, but you move the ball magnet in and out, and you can produce the induced voltage and induced current. In this slide, we are going to study actually the same principle, but it looks a little bit different, but the principle behind is actually the same. So let's look at the left-hand figures first. So you still have a wire connected to the galvanometer, which is not a power supply. They just help you to detect the direction of current. And now you have the U-shaped magnet. And what you're doing is you're moving the U-shaped magnet up and down such that the magnetic field surrounding around the wire will be changed. So intrinsically, this is exactly the same as the previous slide. So you change the magnetic field by pushing and pull them back and forth. Now, you will find out exactly the same thing will happen if you have the U-shaped magnet fixed, but you try to move the wire up and down within the magnetic field. In that case, you still can produce an induced voltage and induced current. So you will say that I'm simply just moving the wire, but the magnetic field is still the same. Why there will be an induced current? The reason is because the magnetic field surrounding around the U shape here is not uniform. So what do you mean? It is stronger here and weak here. So if you are moving your wire up and down, actually you also change the magnetic field surrounding the wire. And finally, how do we determine the directions of the induced current? So let's assume that this is the north pole here on the U-shaped magnet and south pole here. So when you try to move the bar magnet away, so the wire try to attract the magnet back to the original position. So therefore, they will introduce or induce a induced magnetic field with the south pole here and north pole here, try to attract them back. Agree? So if you have the south pole and north pole here, which means you have to produce an induced current moving in these directions, and following the right-hand rule I teach you, they will produce clockwise directions. So you'll find out that they will produce a north pole here and south pole here. Try to attract them back. So intrinsically, we are simply just use the two right-hand rules I teach you in the previous lectures. Now let's have the mathematical formula to summarize what we just learned. And actually, the physics we just studied is basically the Faraday's law. So what is the Faraday's law? It tells you that how big the magnitude of the induced voltage will be produced. So we know that the result depends on the number of the loops of the coil, and also depend on how fast the rate will be changed. So this is a two crucial points. And the magnitude of the induced current actually can be found out through the Ohm's law. So in the previous two lectures, we studied that the Ohm's law is basically V divided by R. So now V is the induced voltage and R is the resistance of the coil. So now you can calculate the induced current through the Ohm's law. Now, how do we formulate the Faraday's law, the induced current, the voltage induced? So it is proportional to the number of the loops, which is the capital N here, and also proportional to how fast the magnetic field will be changed with respect to time, which is the magnetic field divided by the time. So this is the so-called Faraday's law of the inductions. So now you can calculate the magnitude of the induced voltage, and now from the Ohm's law you can calculate the induced current. So please, in the future, when you see this formula, you should remember that capital N here is the number of the loops of the coils, And here, that simply means the change of the magnetic field with respect to time. Now we can use the thing we just learned before. Now try to study Faraday's law again. First is that if you have the induced voltage, which means you create some energy. But where is the energy from? Why there's a voltage difference produced to accelerate the charged particle in the wire such that you have the induced current. So this energy can be understood using the concept of the conservation of energy we learned in the chapter 4 and 3. So what happens is that in the case we just studied, you are the person trying to moving bar magnet in and out. So you are actually doing the work. But the work you did will be converted to the so-called magnetic field energy stored in the device. And this energy will be converted as the electric potential energy. So your work becomes the electric potential energy. And because if you have the electric potential energy, automatically you have a voltage difference. And you all know that there are a lot of electrons within the wire. So once you provide them with some voltage difference, the electrons within the wire will start to move. Then you produce the induced current. And from the lecture we just learned previously, that the more loops, the more electric current will be produced. The reason is because if you have more the loops in the coils, the harder for you to move the bar magnet in and out. So therefore, if you try to move the bar magnet in and out within a bunch of coil, a more number of the loops of the coils, you have to do more work. And when you do more work, which means more electric potential energy will be stored in the device. So for sure you will have more electric current. So that's the reason that when you try to conduct the experiment, which you're only going to do that through the video in the next week, you will find out it is much more difficult to push the magnet into the coils when the number of loops of the coils become a lot. And it is because if you try to bring the bar magnet in, you try to break the equilibrium, yeah? And the nature, as I just mentioned, do not like the equilibrium be broken. So for example, if you have the North Pole here and South Pole here, so when you try to move the North Pole in, there will be an induced magnetic field try to stop you from entering into the coils. And this tendency try to stop you from moving into the coils is the resistance they experience. And that's the reason why you feel it is much harder to push the magnet into the coil. So now let's have the third conceptual quiz. So if you follow the previous discussion, then you will find out that actually the repulsion is from the magnetic field you produce. What do you mean you produce? You will produce an induced magnetic field. Try to fight against to the change of the magnetic field. And Faraday's law can also very useful. And I'm going to give you several examples how they can be applied to our daily life. The first is that when you are speaking or singing through the microphones, how does the voice will be transmitted into the electronic signal and be propagated outward through the amplifier? So what happens is that when you are speaking, you produce the sound wave, and this sound wave will propagating into the microphones, and they will try to oscillate the coils. So the coil will vibrate back and forth. But if you don't have the magnetic field within the coils, then actually it will cause no signal. But intrinsically within the microphone, they will have a magnet within inside, which is stationary, and with the coils surrounding around them. So your sound wave will vibrate and oscillate the coils back and forth. And that is actually the pictures I just showed you here. Yeah, you try to move in the coils up and down, but the magnetic field is fixed. You still can produce the induced current in the case. So therefore, when you are speaking, depending on how loud you are speaking, they will determine how strong the vibration of the coils it will be. Then it will determine how big the induced voltage and induced current it is. And this induced current will flow into the amplifier, and people can record the signal, and people can hear your voice with even louder voice. The second example is the electric guitar. So it is pretty cool to see someone playing the electric guitar. But what is the principle about that? Why simply just vibrate the string along the guitar can produce the voice? So when we say the electric guitar, the principle is that the string actually is made by the metal, and part of the string of the guitar is magnetized. So they have north and south pole there. And next to the string with the magnets, they have the sensor. And once again, this is the bar magnet. But in this case, this bar magnet is fixed over there. So what will happen is that when you play the guitar, the string will vibrate back and forth. Yeah? So when they vibrate back and forth, they will produce an induced magnetic field here. Depending on how strong the string is vibrate, you can determine how strong the induced magnetic field here. And this change of the magnetic field will produce an induced current again. Then now this induced current will connect it to the amplifier and become the voice you hear. So you will find out all the example I give you today, the principle is still the same. You either just moving the wires or moving the magnetic field. So the next example about the Faraday's law is that before you was born or when you was a kid, when people listen to the music, they are listening to the so-called magnetic tape. So the message recording in the tape is also following the similar approach. So the tape is magnetized with the north pole and south pole, but they are not as smoothly magnetic fields distributed there. Instead, it is a gap. So part of the magnetic tape is magnetized, and part of them is not. So when you try to flow the tape within your recorder, and they were interacting with the magnetic field here. So when you have the tape flowing through, you basically change the magnetic field here. So when you change the magnetic field here, you will produce an induced magnetic field with the induced current. So that's the reason that now if you put the tape in your recorder, they can play the music because they are keep rotating the tape. And when you rotating the tape, you change the magnetic field, and the magnetic field will be converted into the current and as a message and be played as a music. So now let's have our last conceptual quiz today. So if you have a car, for sure made by the metal, and moving in a wire, a loop. Now, because we have the magnetic field of the Earth, so how strong the magnetic field of the Earth within the loop will be changed? This is the first question. And the second one is, will this produce a change of current? And the answer is yes. It is because of that when the magnetic field has been changed, you will produce a change of magnetic field.